Good morning, students. In the last class, we discussed about the Rutherford atomic model. Okay, so in that Rutherford atomic model, we are to continue with the same today. Okay, so what are the observations? Means initially I'll explain that. So he arranged a beam of light which emits the alpha particle, and he made them to pass through the lead plate. Okay, in that the small holes are made. So and again the gold foil is set up. Around that gold foil, a zinc sulfide screen is situated or designed in such a way. Around that gold foil, the zinc sulfide screen is placed. Okay, so then what happens when we allow that alpha particles to fall on that gold foil and they start emitting the radiations. Okay, when alpha particle strikes the gold foil, they start eliminating a radiations. So that radiations of what? Those are alpha particles only. So what is that observations means? In that observation, so here what he observed, I'll write here. So in that observation, first one is some are undeflected. Okay, some are deflected by small atom and some are deflected exactly 180 degree. So exactly 180 degree means they are bounced back. Okay, so these are the observations done by that experiment. What is? Some rays are undeflected, some are deflected by a small angle, and some are exactly bounced back at a 180 degree. Means they are exactly reflected. Okay, so that is what observation. So from this observation, what he concluded? What is its conclusion? So as I told you, why these? If we consider the Thomson's atomic model, according to the Thomson atomic model, he said that positively charged species or new protons are uniformly distributed throughout the atom, and only the negatively charged species, that is electrons, are trapped between them like a watermelon. I told you. Okay, so if we consider that as a atomic model, because initially he only proposed. Okay, so by his theory he is going to describe or he conducted an experiment based on that atomic structures. Okay, so then what happens if the Thomson atomic model is correct? Then here the first condition, some rays are undeflected, that should be wrong, because each and every radiation can come in contact with proton in any one of the atom. So here I told you this is the Thomson atom, positively charged or uniformly distributed. Uniformly means of course they are throughout the atom. If throughout the atom, if any rays is passed through this type of model, of course they will get deflected. Okay, but in the Rutherford atomic model, the first thing what is observed, some are undeflected. Some alpha particular rays are undeflected. What is the reason for that? The reason is the atom has lot of empty space. Atom has lot of empty space, and still we don't know what is the place is, why it is empty. Okay, next, these two, some are deflected by small angle and some are deflected exactly 180 degree. Okay, so listen, some are deflected by small angle and some are at 180 degrees. These atoms mass is concentrated at a point. Okay, this atom's mass is concentrated at a point. Concentrated means collected. Okay, so if this is the atomic structure, including the atoms, here this is the nucleus. Means all mass. Mass, as I told you, the mass is always the protons plus neutrons. Number of protons plus number of neutrons. So number of electrons are never involved in the weight of the atoms or mass of the atoms. So listen, so the mass is concentrated here. They are in a small size. This is called nucleus, which is consists of protons and neutrons. And I am telling you, here at that time neutrons are not yet discovered. Of course discovered, but it didn't consider protons, so neutrons inside it. Okay, inside the nucleus it didn't consider. It considered only positively charged species are concentrated in the nucleus. Electrons are revolving around the nucleus. Okay, so from these two, what we concluded? These atoms' mass is concentrated at a point. That's why when the waves are passing nearer to the nucleus, then they are small, deflected by a small length. Okay, when they are exactly strike this positive charge like this, if they are passing nearer to each other, they slightly bounce back. When they exactly falls on the nucleus, there is no space. They are repelled. Repulsion force will be there, so they will bounce back in the same direction. Some are like that. Some are deflected, some are undeflected, and some are bounced back. So this is the conclusion by these calculations. Okay. So then after that, how he suggested the model. Okay. This is the conclusion. This is a model, atomic model. So in that atomic model, what is this conclusion is? The positive charge and most of the mass of an atom is densely concentrated at a point. This is the first thing of the model. Next, second one, electrons are revolving around the nucleus in a path called as orbit. This one is important. What is orbit? Okay. Next, third one, the volume of the atom, the volume of the nucleus is negligible compared to volume of atom. So these are the postulates are the things which we are going to observe in the Rutherford atomic model. Okay, so first one is the positive charge and the most of the mass of an atom is densely concentrated at a point, and that point, okay, that is called as right here nucleus. Okay, so the electrons are revolving around the nucleus in a path called as orbit. Next, the volume of the nucleus is negligible when it compared to the volume of the mass. Here I told you. So if this is the atom, electrons may be revolving around this. So no matter how many shells are there, the nucleus is here only. So if this is the size of atom, so then this is very negligible compared to size of the atom. That is what the last thing they concluded. Okay, so this is the model suggested by Rutherford. Okay, so students, as I told you, of course he suggested this and he awarded Nobel Prize also. But even though this theory is presently we are, as I told you, following which model means quantum atomic model. What is the reason? Because this model is also wrong. He never successfully explained some criteria of the atoms. So what are those criteria? What are those drawbacks means? So I'll take here drawbacks of. Okay. So before going drawbacks, I'll say. So from this Rutherford concept, we can get an idea of isotopes and isobars. So from that we can easily say atomic number and the mass number. As I told you, at that time, protons, neutrons and electrons are already discovered before conducting this alpha scattering experiment by Rutherford. So listen, what are isotopes, what are isobars means in the last previous chapter, I already said in the previous. I hope in some basic concepts of chemistry, I already told you. Isotopes means, okay, the atoms having same atomic number, okay, different mass number. Those are called as what? Isotopes. Compounds having same atomic number, different mass number. Now the thing is, what is atomic number? What is mass number? Okay, so students remember, if I represent this one is that, this one is Z, this one is A. So you often say that any element is represented in this manner. This is the symbol of the element, this is the atomic number, this is the atomic mass, means mass number. Okay, so listen here, I will take helium here. Helium is the symbol okay, of the element. Here it is 2, here it is 4. So this is the atomic number, this is the mass number. So I write here, number of electrons is 2 we know, number of protons is 2 we know, and the number of neutrons is also 2. How can we say? So listen here, we consider this one is as atomic number, protons and electrons are always equal, and the neutrons may be same or different. So in this boron or beryllium, it is 4 and 9. Here the number of electrons are 4, number of protons is also 4, okay, but the number of neutrons are 5. So neutron number may be equal, may not be equal, but always number of electrons and number of protons are equal in a neutral molecule. They are not a charges, it is not B plus, He plus, it is not like that. They are not charges, they are neutral molecules. So in the neutral molecules, number of protons and number of electrons are equal always. Okay, and remember here, so this one is of course, as we know, this is number of electrons and this one is number of protons plus neutrons, but that is wrong. Because in the previous class I told you, the electrons don't have any mass. Understood? They have only charge, they don't have any mass. So how many number of electrons are present in the molecule? They won't affect the mass of the atom. So the mass of the atom is purely explained by calculated by nucleus. In nucleus, protons and neutrons are there. Understood? So here this is the number of protons. What is atomic number means? It is not like number of electrons present in an atom are called as atomic number. That is wrong statement. Initially, still we know. So the number of electrons is nothing but atomic number, but it is not number of electrons. Because in Na plus, number of electrons is 11. Even though atomic number is how much? Sorry. Atomic number is 11. Okay, so protons are 11, electrons are 10. That's why it is Na plus. Even though we are considering this atomic number as 11. Na plus atomic number is 11. Sorry, but the number of electrons is 10, number of protons is 11. So if if it is equal to the proton, instead of proton, if it is equal to electron, listen here, Na 11, 23. Assume here, this is number of electron. If one electron lost, Na plus, then it must be 10, 23. Then number of neutrons will change. Here the number of neutrons is 13. Here, 12. Here the number of neutrons is 13. Can any atom accept or donate and subatomic particles? Means it is not possible. If here 11 protons are there, 11 protons only there. Only electron exchange takes place, not proton and neutron, because they are concentrated in the nucleus and it is highly stable. Electrons are revolving around them, so if they are far away from the nucleus, then the force will decrease, then they can easily remove by applying extra energy. That electronegativity, ionization energy, I told you. Correct? So here, if you consider this one as number of electron, there is a change in proton. In Na plus as well as Na, number of protons and number of neutrons are same. So what is atomic number? Means it is the number of it is the number of protons in an atom. Okay, that is called what? Atomic number. But here you can write in star mark, that is not number of protons is equal to number of electrons. If the number of protons is equal to number of electrons, means, so that's why we may change this. What is the atomic number definition? It is the number of electrons in an atom in a neutral state, or number of electrons in a neutral atom. You have to mention neutral atom if you consider electrons. If not electrons, we can easily say it is the number of protons in an atom. Next, what is mass number or atomic mass? Okay, so it is sum of protons and neutrons. Protons and neutrons in an atom. You may write in the nucleus also you may write. Number of protons and neutrons in an atom is called as mass number. So students, this one is represented by Z, this one is represented by A. Okay, this one I write here. Number of protons always equal to Z. Number of electrons also equal to Z. So number of neutrons. Okay, so that neutrons is equal to A minus Z, because this atomic number nothing but sum of protons and neutrons. If we subtract the protons, we will get the number of neutrons. Initially what I did here, so in beryllium 4 9 means your number of proton is 4, electron is 4, neutron is 5. I wrote that. How? Because 9 minus 4 is 5. mass number minus atomic number. That is 5. So this is what the atomic number and the mass number idea we can get from this model. Rutherford atomic model. Atomic number and the mass number. Atomic number is number of protons present in an atom. Mass number is number of protons plus neutrons in an atom. Represented by this. And this is the formula to calculate number of protons, neutrons, and electrons. Okay, so from this atomic mass and the mass number, we can explain isotopes and isobars. So students, I just write the example here that you can easily understand. So for isotopes, example is H11, H12, H13. So H11, H12, H13. So this one is protium, deuterium, tritium. So in protium, there is no neutron. Listen here. In this one, proton is 1, electron is 1, neutron is 0, 1 minus 1 is 0. So in this, proton is 1, electron is 1, neutron is 1. So here, proton is 1, electron is 1, neutron is 2. Okay? So listen, you can also say the definition for these isotopes. The compounds having same protons, same number of protons, same number of electrons, but different number of neutrons. Isotopes means you may say compounds having same atomic number or the elements having same atomic number 1, 1, 1 and different mass number. Okay, what is this atomic number? It is the number of protons. Okay, so you can also say the definition. The elements having same number of protons and electrons but different number of neutrons are called as, what is it? Isotopes. Okay, so this is the best example, protium, deuterium and tritium. So another one you may say C13, C612, C613 and C614 is also there. In that the atomic number is 6, the mass number is 12, 13, 14. Here the number of proton is 6, here the number of neutron is 7, here the number of neutron is 8. So you may calculate by using this. Okay, so another one is isobars. So students, what is this isobars means? I'll give example, then you will understand. Argon 20, argon 18, 40 and calcium 20, 40. These two are example for isobars. What is same here? This one. Mass number. What is different here? Atomic number. Means the atoms having same mass number, different atomic number. Then they are said to be isobars. These two are the example of isobars. Here the mass number is same, 40, 40. Of course, in this, both electrons are different, protons are different, as well as neutrons are different. So listen, in argon, proton is 18, electron is also 18, neutron is proton is 20, electron is 20, neutron is also 20. So in both the case, protons are different, neutrons are different, as well as electrons are different. So we cannot say them like they are having same that this and like that. Okay. So of course they are having same mass number but different atomic number. That is called isobars. So from this Rutherford model, we can have the elaborate idea about this isotopes and isobars. Okay? Listen. So this is important. What is atomic number, mass number, isotopes and isobars? That much is enough. Okay? Students, next one is The drawback of this Rutherford atomic model. Why this model is failed? Why we are not accept this model like that? Okay. Okay. So students, the thing first initially after suggesting this model, we compare this model with solar system. Compare this atomic model with the solar system. So what is that? The nucleus which is concentrated at the center of the atom, that we considered as what? Sun. Okay, nucleus is considered as sun, and these electrons are revolving around that nucleus means considered as planets. So you compare this atomic model, Rutherford atomic model is also called as solar system model or solar atomic model. Why? Because it is compared with the solar system. So you consider the nucleus as the sun and the electrons are the planets, and they are keep on revolving around them. Okay, of course students, these are electrons means of course when they revolving, they accelerate. Okay, when they accelerate, then they possess energy of. Okay, when they accelerate, the force is equal to, okay, are directly proportional to charges Q1, Q2 divided by R square. Electrons are there, as I told you. That electrons, the two or more electrons are there, that is considered as Q1 and Q2. Okay, they are revolving around the nucleus means of course, as I told you, electron is here at initial point, next is here, like that. That position is Q1, Q2 like that. Okay, to remove the proportionality, we can get K, Q1, Q2 divided by R square. So Q1, Q2 are the Coulombic charges and R is the distance between the charges. So when they are revolving in the orbit, okay, they'll experience, and so they are in the acceleration. When they are in the acceleration, of course, they experience a force. That force is directly proportional to Q1, Q2 by R. So this is compared with gravitational force. Okay, so gravitational force is equal to G into M1 M2 by R square. Both are same. This is what? Fg. This Fe. Electrical force. This is gravitational force. G is the gravitational constant. K is the electrical what? That is the constant. This is also constant. Q1, Q2 are charges. M1, M2 are masses. R is the distance between them. So this is applicable for what? The solar system. Gravitational force, you know, the solar system is mainly stable due to what? Due to the force of the gravitational force of the star and the planets. You know that. Earth is also having the gravitational force. Moon is also having. Okay, that another planets, it may be Mars, Mercury. Those are having their particular gravitational force. Okay, so this charge force, as I told you, this is compared with the solar system. That is compared to what? Gravitational force. Okay, so students, when it is compared to that, you know, when the planets are revolving around the sun, they won't experience. Of course, they emit radiations, understood? But they are not that much harmful. Okay, they are not creating any disturbance. But in the atom, if the electrons are revolving around them, they emit electromagnetic radiations. Electromagnetic radiations. When these are in a force, or when the electrons are in an acceleration, they emit electromagnetic radiations. Okay, so another one is. So they are, okay, as I told you, when they are possessing that electromagnetic radiations, even though, listen, if anything, any metal is there or any species is there, atom is there, if it keep on emitting energy, Electromagnetic radiation means nothing but that is energy. If the any atom keep on releasing energy means it should what is that? Lost its stability. Understood? If anything keep on releasing energy, it should lose its stability. But these atoms never loses their stability. Understood? So I told you, if we are keep on using our energy, we will be low after some time. We will feel so tired after some time because we lost our energy. Similarly, these are also when they emit radiations, electromagnetic radiations, they are in the energy form. When they emit energy continuously means, so they may lose their stability, but they won't lose their stability. So this Rutherford fails to explain the stability of the electrons around the nucleus. So what is the drawback here? I write. He fails to explain stability of atom. Okay? And another one, students. So you know, so many electrons are there. Okay? Some are energetic, some are non-energetic, less energetic, some are more energetic. So these you only consider. So the electrons are revolving around the nucleus in a path called as orbit. It does not explain how successfully these revolve around the nucleus, what are the orbits, what are their energy. Okay, so it fails to explain energy of the electrons in different orbits. So another one is it fails to explain energy of electrons. Okay, and he said in the atomic structure, nucleus is energized. And he said the nucleus is energized, but in the atomic model, the electrons are energized than this nucleus because protons and neutrons are not involving any chemical reactions. The chemical reactions of the species is mainly due to what? Electrons. By the loss of electron or by the gain of electron, they show different chemical properties. But in the nucleus, it is of course stable base. When it is stable, so listen, stable means you cannot think they are highly energetic. If highly energetic, they are unstable. If it is having less energy, then it is stable. In the atoms, which one is having less energy, that is stable. Which one has more energy, that is unstable. So compared to electrons, nucleus are least in energy. But he said nucleus are energized than electrons. So due to these three reasons, this Rutherford atomic model is rejected. Later, initially it is accepted, of course he awarded the Nobel Prize. Later it is rejected. When it is rejected? When the another scientist Niels Bohr worked on this atomic model and he proved the Rutherford atomic model is wrong and what I experiment, he conducted an experiment and what I suggested that atomic model is correct. When the Bohr introduced the new model, then this model is rejected. This law is rejected. Understood? So this is what observations, conclusion, the structure of model and the drawbacks, these are all important. That's why I wrote it on board in a single. Next one is, as I told you, so from this Rutherford atomic model, okay, Bohr took up points and we worked on that. So that is called as leads to the discovery of Bohr's atomic model, or we may also say developments leading Bohr's atomic model. result. So developments leading Bohr's atomic model from the Rutherford model is, so that is dual character of electromagnetic radiations. First one is dual character of electromagnetic radiations. Okay, and the second one is experimental result of atomic spectra, which is only explained by assuming quantized. These are the two main things that leads to the development of Bohr's atomic model from the Rutherford model. As I told you, in the Rutherford model, I told you, so when the electrons are revolving around the nucleus, they emit electromagnetic radiation. Okay, so this Neil Bohr observed that electromagnetic radiations movement, the propagation of the electromagnetic radiations. Okay, so then they came to know, so this electromagnetic radiation dual characteristic. Okay, what is the dual characteristic? Sometimes they behave as wave, sometimes they behave as particle. Okay, these electromagnetic radiations sometimes behaves as wave, sometimes behaves as particle. That is what dual nature of the electromagnetic radiations. And another one thing is the experimental result of atomic spectra, which only explained by assuming quantized. So this quantized means nothing but quantum is the energy, the pack of the energy packets there. Quanta means they are the energy packets emitted by a particles. Means when the electromagnetic radiations is behave like a particle, they emit energy packets called as quanta. So when quantized, then only we can observe this atomic spectrum. So the atomic spectra is explained by only particle nature of the electromagnetic radiations. So these two main topics tells about what is that? Give a lead to the Bohr to develop its atomic model. So initially what he did, he studied the wave nature of the light, okay, which is experimentally determined by James Maxwell. The wave nature of light is by Maxwell, particle nature is by Planck's. So by mixing of those two theories, this Bohr explained the dual nature of the electromagnetic radiation. Means the electromagnetic radiation, especially wave nature of electromagnetic radiation, is alone explained by Maxwell. Particle nature of the electromagnetic radiation is alone explained by Planck, by photoelectric effect. Okay, so he considered both the theories and he explained the dual nature of the electromagnetic radiation. So he considered the experiment of Maxwell as well as Planck's and mixed those theories and he developed an atomic model. Okay, so next he also explains, so this James Maxwell explains the electric spectra. Means that gamma rays are there, electromagnetic rays are there, IR rays are there, microwaves are there, radio waves are there, visible region is there where we can see easily the things. Okay, so in the visible range only we can easily see things in our naked eye. We cannot see ultraviolet, we cannot see infrared. but we can see only the things in visible region. Those are what, how they are classified based on their different wavelengths. Okay, that is what wave nature and the particle nature. Just remember these two, the leadings to the development of the Bose model. So in the tomorrow's class, I will explain the wave nature of light, sorry, electromagnetic radiation and particle nature, and later by mixing up with those two theories, I will explain Bohr's atomic model. Okay, so for today's class, this is it. Thank you.